Hello everybody. In this video I will start by showing the Fourier transform and its properties. Let us start with these slides showing that a periodic function ft, which has a period t, has a Fourier series expansion sum k minus infinity to plus infinity ft exponential minus j k omega 0 t, where omega 0 is 2 pi divided by the period t. In the subplot B, we see the same function ft, but with a period which is greater than the first period t1, and the t2 is shown to be 4 times t1. In the third subplot, we see that the t0, or the period of the function, is extended to plus infinity. So we can see the ft of a short duration, capital T, can be seen as a no periodic function or a periodic function of a period equal to plus infinity. So we can say that a no periodic signal can be seen as a periodic signal when the period t0 goes to plus infinity. Starting from the definition of the Fourier series ft, it is the infinite sum k from minus infinity to plus infinity ck exponential j k omega 0 t, and the coefficients ck are obtained from the formula 1 over t0 integration over the period t0 ft exponential now minus jk omega 0 t dt. We know that the k takes values in the set z, the set of integer numbers. So if I will focus on two successive frequencies, k omega 0 and k plus 1 omega 0, and I will make the difference delta of omega, which is the difference k plus 1 omega 0, minus k omega 0, we will see that the result is equal to omega 0, which is by definition the 2 pi over t0. So the variation of omega is constant because the k took values in the set z, which is the set of integer numbers. But if we replace k by a real number, we will see that the difference will not be constant. It will be dependent on k, which is in this case a real number. So how can we see the omega 0, which is by definition 2 pi over t0? It is d of omega. If I will tend t0 to plus infinity, so the 2 pi over t0 will be equal to d of omega, which is a variation of omega when the period t0 is extended to plus infinity. So for instance, if we admit this definition, we will see k omega 0 as the true continuous variable omega when k takes values in R, which is the set of the real numbers. According to these new definitions, we can set k omega 0 equal to omega when the period is set to plus infinity, and ck takes the new formulation. So 1 over t0 I will multiply by 2 pi and I will divide by 2 pi, and integration over one period I will take it from minus t0 over 2 to plus t0 over 2. So here I will get an integration over one period of time, and I will replace the variable k omega 0 by omega, which is the continuous omega that will take values in R. So after this substitution, we will see that this term, it is replaced by the term between brackets, and the 2 pi over T0 will stand for the variation of omega, noted d of omega, and I have, of course, a coefficient 1 over 2 pi, which is appearing here. So now the term between brackets, we will call it the Fourier transform of ft, which is simply a complex number that results from integration with respect to time of the function ft exponential minus j omega t. So we will define the Fourier transform of ft. F calligraphic of ft stand for the Fourier transform of ft, and it is of course a function which is dependent on omega, and it is the integral from minus infinity plus infinity ft exponential minus j omega t dt. And from the Fourier series definition, we have ft equal to the discrete sum from minus infinity to plus infinity 1 over 2 pi, and the term between brackets, which is the ck, is now replaced by this term f of omega over 1 over 2 pi d of omega, and of course I will multiply it by exponential j k omega 0 t. K omega 0 will be replaced by omega, we see it here, and the discrete sum will be replaced by a continuous sum from minus infinity to plus infinity. So the ft now, it is 1 over 2 pi integral minus infinity to plus infinity, the Fourier transform of ft, exponential, now you see, plus j omega t dt. So we can see it as f, I will return back to my f by applying the inverse Fourier transform of f of omega. Okay. The existence of the Fourier transform is related to some conditions that must satisfy the function ft. So on any finite interval, ft should be bounded. Ft should have a finite number of maxima and minima. And of course, ft has a finite number of discontinuities. And ft should be absolutely integrable from minus infinity to plus infinity. It means the value of this integral should be bounded by certain coefficients, and we note it less than infinity. It means it takes a limited value. Remarks that all these conditions are similar to the conditions of the existence of the Fourier series. I will call energy signals any signal ft that meets the condition of the boundedness of the energy, which is integral minus infinity plus infinity, ft elevated to the square dt, which is the L2 norm of ft over an infinite interval of time should be bounded. So any signal satisfying this condition is called an energy signal, an energy signal. If we take, for example, the case of a rectangular, the rect function, it is bounded and it is existing over a limited support of time. So when we will integrate it from minus infinity to plus infinity, we will get a limited value. So the rect function is considered as what? As an energy signal. Before I move to the next slide, I would like to make some remark about a periodic function. You see that a periodic function cannot satisfy these conditions because the generating function, even it is bounded, it will repeat itself from minus infinity to plus infinity. And if we will evaluate the integral, in most cases, we will get something which is not finite. So periodic function cannot be seen as energy signals. However, if a signal ft satisfied these new conditions, which is the integral over a period of time, so this is 1 over t integral over a period of time of the absolute value of ft squared dt, and if the limit of this quantity is less than infinity, we can say that the signal ft is a power signal. This property can be verified for many periodic signals. So periodic signals can satisfy the power signal property, but they cannot satisfy the property of energy signals. The Dirac function ft equal to a delta of t minus t0. So this function exists only at t equal to t0, and it is 0 otherwise. And the integral minus infinity to plus infinity of delta of t minus t0 dt is equal to 1. Now I am interested in evaluating the Fourier transform of this delayed pulse of amplitude A. So I will note f of omega, the Fourier transform of a delta of t minus t0, which is by definition minus infinity plus infinity a delta of t minus t0 exponential minus j omega t dt. So this delta multiplied by a function will be equal to the delta to this function evaluated at t minus t0 times the same delayed delta, which is delta of t minus t0. Now, if I will integrate delta from minus infinity plus infinity, I will get 1, and I will be left with the quantity a exponential minus j omega t0. And you see that this value is not dependent on time, but it is only dependent on the frequency omega. So this is our Dirac function of amplitude a, and it is existing at t0, which is a delta t minus t0. So its Fourier transform is given by this. And clearly, if I will use the Euler identity, which is cos of omega t0 minus j sine of omega 0 t. So I will have a real part and imaginary part. So the Fourier transform here is a complex number having real part and imaginary part. So the amplitude of f of omega is equal to a. It is clear that this is a complex number written in exponential form, where I have amplitude a, or the modulus of this complex is equal to a, and the phase is dependent on omega, and it is minus t0 omega, minus t0 omega for all omega. When I will replace a by 1, t0 by 0, it is clear that the pulse existing at time t equal to 0, delta of t, it has a Fourier transform equal to 1. So this is the Fourier transform pair of delta t. It means delta t gives 1 by the Fourier transform, and 1 gives delta t by the inverse Fourier transform. Now I will evaluate the Fourier transform of the rect function having an amplitude v, and it is existing from minus t over 2 to t plus 2. Direct integration using the formula of the Fourier transforms gives tv sinc of t omega by 2, and the sinc function is the sine of omega over omega. You see that a limited function in time results by the Fourier transform to what? To unlimited function in omega. Right. Now we will pass to the most important properties of the Fourier transform. We start with the trivial one, which is the linearity transformation. If I have a signal f1 of t, which has a Fourier transform f1 of omega, and f2 of t having f2 of omega as a Fourier transform, how about if I will take the linear combination a f1 plus b f2? What it should be their Fourier transform? Since I have an integral, so the integral of the sum will be the sum of the integrals, which results to a f1 of omega, capital, plus b f2 of omega, where f1, f2 are the Fourier transforms of f1 and f2 respectively. We will use this property for getting the Fourier transform of the signal b cos omega 0 t. We know that cos of alpha can be expanded as a sum of two functions, two complex, exponential j alpha plus exponential minus j alpha divided by 2. So I have, like, if I will replace alpha now by omega 0 t and I will multiply it by b, I will have a linear combination of two functions. So I will compute now b over 2 exponential j omega 0 t, and then I will evaluate the Fourier transform of b over 2 exponential minus j omega 0 t, and then I will sum them using the linearity property of the Fourier transform to get the results, which is shown here as the pair Fourier transform. So now I will keep this exercise to you because it is a simple. So when I will use the definition of the Fourier transform, I will have a multiplication of two exponentials, which is and the integral of the exponential is easy to get. So you can easily prove that by summing the two Fourier transform, you will get these results. We have seen in the previous lectures that if I have a linear time invariant system having an impulse response ht, the output yt, it is the convolution of the input xt by the impulse response ht. We will show now that the Fourier transform of the signal yt, it is in the frequency domain a multiplication of the two spectrums of xt and ht. Let ft and gt be a real valued time dependent function. The convolution product is defined as f star g, and it is by definition given by this relationship. The Fourier transform of yt, which is the convolution product of ft and gt. So I will multiply this function by exponential minus j omega t dt, and I will integrate from minus infinity to plus infinity. Now, since I can reorder the integration process, I can bring fs here, ds, and I will integrate the rest with respect to time, and I will keep s as constant. When s is constant, I will get a function which is only dependent on omega and s. And then I will perform the integration with respect to the variable s by multiplying by the function fs. So now I will do, and I will set a change of variable tau equal to t minus s while keeping s unchanged. It means if I will take d tau, I will get dt for s constant. So here I have replaced the t by the sum t plus s, and I am seeing that the blue term here is an integration of a function which is dependent on tau and s, but integration is performed with respect to t, so I can bring the term exponential minus j omega s to this side, which gives the following results. But I am seeing that when I will integrate, now the time, so here it is dt, I will replace dt by d tau, and I will see that this term is equal to the Fourier transform of gt, and this term, it is the Fourier transform of ft. So the convolution of ft and gt has a Fourier transform equal to the product of the two Fourier transforms that are f and omega and g of omega.